The user interface of the ErrorPro consists of three areas: drawing area, console, and command line. Let's create a system. Let's add element, and using this command we give the name to this element, generator. After that, let's add a data, and we call it gPower, which will be the output data of the generator, and we connect them with a data flow arc, meaning that generator provides gPower. Let's add another element, device, and this element will be the consumer of this gPower. Now let's take a look into the values of gPower. By default, gPower can be either OK or error. Let's rename the names of the values explicitly to has power and no power. And the gPower will be initialized with has power. Now let's specify a failure. We add a failure and we give a failure expression. gPower equals to no power. When there is a no power in this variable, this is a failure condition of our system. Now we mark generator as initial element. The process will start with the generator, and after the generator will execute device. Therefore we add a control flow from generator to the device. Now we compute the probability of failure by clicking to the failure and selecting probability. The probability is 0 because the initial value of the gPower equals to has power. Now let's change the properties of the generator. The properties are specified using prism commands. For instance, the default properties of the generator is if true, then with probability 1, gPower equal to has power. Let's change it and let's specify that with probability 0.99, gPower will be equal to has power, and with the rest probability 0.01, the gPower will be no power. Now, after execution of the generator, there is the probability 0.01 that it will be no power, and we obviously can compute it. Now let's close the control flow loop by adding the control flow arc from device to the generator. After the generator we execute device and generator again, and so on. And in this case the probability of failure will be 1, because eventually we will end up with the failure condition. In such case we can be interested in so-called mean time to failure, or in particular case mean number of steps to the first failure. We computed it and it equals preliminary to 200, meaning that in average after 200 steps we will have a failure. Now let's compute the distribution of the probability over time from the step 0 to 100 with an interval 10. We can see that probability grows from 0 to 0.4, and in the step 100 it reaches 0.4. So 0.4 is rather big probability, and let's improve our system. Let's add another element called battery. We also change the control flow in a such way that after the execution of the generator we execute battery and then we execute the device. Also, now from generator we have a data flow to battery, and we add a new data called bPower. And we connect battery to the bPower and bPower to the device. So basically the power from the generator loads the battery, and then the power from the battery is used for the device. We add another data, we call it bLoad, which will specify the current load of the battery. Okay, we update the values of the bPower, making it like the values of the gPower, either has power or no power. And we are updating the values of the bLoad. And here we use the advantage of the Python language. We specify that the values of the bLoad equal to the list, which contains numbers in the range from 0 to 9, and the initial load will be 5. Let's set up the behavior of the battery. We use the same Prism style commands. Battery has inputs and outputs. So we define the following logic. If the G power, the power that comes from the generator, equal to has power, then we increase the load of the battery. Here we use the construction minimum. This helps us not to exceed 9. Let's say if the B load is bigger than 9, we will still use 9. And in the case if we have a failure of the generator and the G power equal to no power, in this case we have another condition. If we still have the load in the battery, if the B load is bigger than 0, then in this case the B power, the output power of the battery, equal to has power, but we decrease the load of the battery. And similar, if there is no power from the generator and the load and the battery is empty, the load equal to 0, in this case the output power of the battery equal to no power and B load is still 0. Let's update our failure. The failure expression now should be not G power equal to no power, but B power equal to no power. In this case, okay, the probability will still equal to 1 because eventually we will have this failure. But let's take a look into the distribution of the probability over time from step 0 to step 100. We see that the probability is extremely low. It's 1 in the power minus 12 in comparison to the old probability, which equals 0.4 in the step 100. Now let's assume that our generator has a permanent fault. In order to model this, we add a new data G-state and we connect it to the generator. And we set up the generator as follows. If the G-state is OK, then with probability 0.01, generator has a failure, there is no power in the output, and the G-state becomes an error. But if the G-state is already an error, then the generator stays in this erroneous state and provides no power. So we recompute the probability distribution and we see that results are not so good again, because now the probability grows from 0 to 0.22, and this probability is much higher than the previous one. Finally, let's assume that our generator can be repaired after the permanent fault. Therefore, we add another element and we call it repair. We set up the control flow in such a way that after the generator we can switch to repair, and after the repair, once the generator is repaired, we come back to the execution of the element generator. Let's take a look into the properties of the generator. Here we can see that it has also the control flow section, meaning that CF, it means a current control flow. If the current control flow equal to the generator, then we jump either to battery or to the repair. In this case, the probabilities are equal 0.5 and 0.5. It's just generated default probabilities. Let's change this logic and let's specify the following. If the CF, the control flow, equal to generator, and if the state of the generator equal to OK. In this case, we jump to the battery with probability 1. Otherwise, if the G state equals to error, then we jump either to the battery with probability 0.9 or to the repair with probability 0.1. We connect the element repair with the G state and we specify the properties of the repair, that it basically repairs the G state. So also for each element we can specify a parameter time. It is an execution time of the element. By default it's 1. And for the repair we can specify it like 100, like it takes a considerable time to repair the system. And this parameter could be used for the computation of the downtime. We can compute the downtime of the system also from the step 0 to, in this case, we increase the interval to the step 1000 with interval 100. And this plot shows that in the x-axis the execution time and y-axis the downtime of the system, which grows with an execution time.